This meeting is being recorded.
Yeah, let's just do that. That'll be easier. All right, so I guess a couple announcements before we actually dive in. Most obvious announcement, there's a midterm Thursday. It's at 7 p.m. Another question in the chat, if it's going to be recorded, where will it be uploaded? It will just be shared like in the course staff Slack channel. It won't be shared with students, but it's just a note that like you literally are being recorded, but it's not going to be shared except amongst the individual TAs. So sorry for the confusion there. So as I was saying, there's a midterm. It's Thursday, 7 p.m. Pacific, unless you requested for alternate time to take it at an alternate time. There's a homework out. It's due Sunday night, and then this lab is due tonight. And I think that's pretty much it. All right, so I just want to make sure that you guys can see my screen. A quick yes in the chat, or like a thumbs up on your little thing. Let's. Okay. Yeah, I think a couple people were unmuted, but I've gone ahead and muted everybody else. So hopefully that resolves the echo. So I guess let's get started. First thing we do, we initialize the auto grader that everyone loves. So it looks like transformations and KDEs. That's what this lab is about. This lab is kind of about the math behind visualizations. It's how we can kind of modify our visualizations to make them look better, so to speak, in simple terms. So it says practice plotting, applying data transformations, working with KDEs. Awesome, awesome, awesome. We import our modules, pandas, numpy, seaborn. That should all look very familiar. This lab, we're going to be using World Bank data. We're importing it into a data frame here. This cell is given to us. Looks like we have a row for a bunch of countries, a bunch of different metrics, primary completion rate, whatever that means. So it looks like we have a lot of nice columns here. We can list out the columns. GDP, purchasing power, students, mathematic proficiency, great. So it says in the first part of the assignment, we will look at the distribution of values for female adult literacy rate, as well as the gross national income per capita. The code below creates a copy of the data frame that contains only the two series we want, and then drops all rows that contain null values. So if there's no data, we just drop it. There's a note here that's pretty bad, because a lot of times null values are still kind of worth investigating, as you saw in the project with like bad zip codes. But just for the sake of this lab, it's easy, it's a quick lab. We just drop them. And then helpful here, we rename the columns. So instead of typing out this whole long annoying string, we just say lit or ink. And before I continue, looks like there's a question in the chat about the midterm. Will midterm 1 be about as long as the midterm from spring 20? That's kind of hard to say because I don't know exactly how long the midterm from spring 20 was designed to take. But this midterm, it's designed to take, it's designed to be completed in an hour and a half. So I think it might be a little bit shorter. I'm hesitant to say, but yeah, it shouldn't be too long. Yeah, the spring 20 would have been a lot longer because it was a checkpoint assignment. So what we did is we gave everybody a full 24-hour period to do it, and you could work on it for as many hours as you wanted out of the 24. So it probably would be, yeah, it's fair to say that the checkpoint was probably a lot longer than the other midterm. So this one will be shorter. Can we have these questions after the lab walkthrough? Yeah, okay, yeah, fair enough. We'll save midterm questions towards the end. Yeah. So Sufang asks, what means in place equals true? So when we drop NA here, that means that we are dropping the rows with null values in the original data frame, and we don't have to assign it to a new data frame. So what we could do instead is we could do something like this. And that would work just the same. But we don't really, because this would create a new data frame, which we would then just assign back to df. But it's a lot easier sometimes just to do that. Destructive method, yes. I don't understand quite exactly what that means, but basically you will modify the original df. So a lot of times it's kind of dangerous to use in place. In this case, it's not really a big deal. But a lot of times it's a good idea to do that instead. But it really doesn't matter. Any other questions about this little block of code here, this cell? Let's do. So we see there were 216 countries in our original data frame. Looks like quite a few countries had missing data, so we're only down to 147. That's not that great, but again, this is just a lab, doesn't really matter a whole lot. And we can see the head of our data frame like so. So we have, for each country, we have a lit column and an ink column. So for question 1A, suppose we wanted to build a histogram of our data to understand the distribution of literacy rates and income per capita. We can use CountPlot and Seaborn to create bar charts from categorical data. So this cell was already given to us, so we can just run it. At least I hope we can just run it. And there we go. So maybe I can zoom in a little bit. Well, that just defeated the whole purpose. So here's our count plots. And it says in the cell below, explain why CountPlot is not the right tool. So if people want to chime in the chat or unmute themselves and throw out a reason, just some reasons why this is not that great of a visualization. Someone says you can't read the x-axis labels. That's perfectly, perfectly valid answer. All the labels are cluttered together. You can't really see what's going on here. That's one thing. There's likely overplotting, exactly. What did these things down here mean? You can't even read them. There are too many categories, someone says. That's a really good answer too. When we do CountPlot, we have one category for each of these individual numbers. So if someone's 18, if a country is 18, then that's its own category. And if someone might maybe 18.1, then that's its own category too. So we have lots of categories that we don't really need. Also, it doesn't make sense to count the count of adult literacy rates. Yeah, basically exactly right. It doesn't, we don't really care how many countries might have exactly an income or a literacy rate of whatever it may be, of 13,400. Like you see here, especially the one on the right, pretty much every category, with the exception of a few, has just one country, and you can't really tell what's going on. So we can just write here, can't see axis labels, categories don't make sense. Great. Any questions, any lingering questions about 1A? All right. If not, we'll move on to 1B. So it says, in the cell below, create a plot of literacy rate and income per capita using the distplot function. As above, you should have two subplots. So we kind of have the same setup here, except now we're using distplot. And it says, note here, use distplot, set KDE equals false. There's a big hint here. Always read the hints. Copy and paste from above to start. Okay. So let's copy and paste. And if we run the cell, I don't know why it's taking so long to run, but we'll see the exact same plots. Any thoughts on how to modify this code such that we answer the question? Pretty straightforward, but people want to chime in the chat. What about this do we need to modify? Yep, Simon says use displot instead. Perfect. Not super intensive here. So what displot will do as opposed to count plot, displot is primarily used for when we have like a numerical distribution, so to speak. So this is numerical quantitative data. It's not really like categorical data. If it was categorical data, we could use count plot, but it's not. So we'll use displot instead. And then as Joshua says, yes, set KDE equals false. And then we see some nice histograms. This data is obviously a lot more clean. It's a lot more understandable, readable. We can actually see the distribution of literacy rate or gross national income. A little minute detail here, but I don't really like how these labels like slightly overlap here. So just a little trick that you may not have known of. You can put new line characters in your label calls. So we can have prettier labels that look like this. So a couple questions about KDE. KDE is the kernel density estimate. We'll explore KDEs in like the second portion of the lab, but I can just show KDE equals true. If we left KDE equals true, it would just show like a smooth estimate of our data. So here we have bars. This is a line. And I think actually like that's probably, I think in the next one of the next questions, we set KDE equals true. But for now, we just want to look at a histogram and ignore the density estimate. Yes, someone says just showing the density curve, exactly right. So there we go again. You should see histograms showing the counts. Great. Says displot uses this heuristic called this whatever it is to automatically identify the best bin sizes, although it's possible to set the bins yourself. So these bins look pretty good. Personally, I like to set my own bins because a lot of times these don't really follow like exactly like even numbers. So they don't really make that much sense to me. But it's not super important, especially for this lab. But just know that these bins are automatically generated. So question, displot versus count plot. Displot will show, at least generally, it will group, I don't want to say group because they're all group by. But it will just kind of bin each of these countries into their own category, and then show a histogram, whereas count plot pretends that each of these values is categorical data. So even like when we see a number, normally we expect like numerical data, but count plot, for example, if these were like descriptors or like continent or something, then like Asia, Europe, and so on, then yes, let's go ahead and then we would see, then count plot would make a lot more sense. Does that kind of answer the question about the count plot versus displot? Perfect. So what's the y-axis in the case where KDE equals false, like we have here? This is just count, the number of countries or the number of data points that fall into these bins. So perhaps the question should have been a little bit more explicit about this, but we can do, if we want to be proper about it, we can just set that, and then now we have a nicer, more informative plots with the Y labels. Okay, great. Any questions about this part? Any last questions? All right, for the sake of time, if you have them, just ask them in the chat and we'll get to them at some point. So this next part, in the cell below, try creating the exact same plot again. but this time set the KDE parameter to false and the rug parameter to true. So we set KDE equals false, but now we have this new parameter called rug, which we can set equals true. And it's basically the same as before, but now we have these little dashed lines down here. They might be a little bit hard to see on your screen, but there are like blue like tick marks sticking out. Does anyone care to share what they are? Venture a guess as to what these are, either in the chat or over the air. Yes, someone chimes in, each observation variable, the actual data points, 1 tick for each data point. Yes, exactly right. So each of these ticks represents an individual country. So here they're actually a little bit more spread out. Here they're quite clustered together. So yeah, so this just shows each individual observation. Can be useful, especially if it's kind of down here and not really super like, it's not taking up a lot of space on the plot. So you could easily ignore it if you wanted to, but in case you did want that information, you could look down here and see. So this is called a rug plot. Someone asks, do we usually do rug equals true to see the specifics of the histogram? Yeah. You won't see rug plots a lot. Like I had no idea what a rug plot is before this class. But it is nice to see in case you want to get an idea of where the actual data points lie. And it just provides more information, which is usually a good idea. So yeah, it says you should see the little, maybe, yeah. I asked and it was probably right here. You should see little lines corresponding to actual data points. Let's do one last tweak and set KDE equals true. So set true, true. And this is exactly what we saw before with now the density estimate. Little quirk here, I don't know why this is in the other plot like this, just a matplotlib quirk. These units, they aren't super important, at least not right now, but they are kind of like the density units. So in this case, it means that 5% of the data fall into this bin. Whereas before, when we set KDE equals false, it was just the count. Yeah, someone says the rug plot would be nice if we had really big bins. Yes. But then if you have really big bins, then you might just end up just having smaller bins. Might be the solution there. Okay, so then that kind of concludes 1B. Observations, you'll see y-axis is no longer the count. Great, great, great. So now we get to kind of a more important part, which I'll try to go a little bit faster through. We spent a lot of time on the previous questions. But it says, looking at the income data, it's difficult to see the distribution among low-income countries because they are all scrunched up at the left side of the plot. And that's true. If we go here, this plot on the right, we don't really know what's going on here. We just know there's a lot of countries there, but we don't know much more than that. They're kind of all grouped together. There's a lot of countries there, all clustered together. We don't really know. So it says, yes, the KDE also has a problem where the density functions has a lot of area below zero. Yes, Farhad asks, should the label for the y-axis still be count? No, it shouldn't. It should be density. I was too lazy. Yes, that would be more accurate. Thank you. So if we're coming back here, it says, when we logarithmically transform the ink data, that gives us a more symmetric distribution of values. This can make it easier to see patterns. In addition, summary statistics like the mean are more stable with symmetric distributions. So right now, this is pretty skewed. Sometimes dealing with skewed data is problematic. So they suggest doing a log transformation. So we can kind of just copy this code from above. If I want to do a log transformation of this data, how would I do it? Just using this code that I have now. What would I add to it? Anyone want to chime in? Great, yeah, bunch of answers coming in. They all look essentially correct. We can just wrap df inc, just wrap np.log10 around it. If you wanted to, you could define a new series, a equals np.log or whatever, but it's just easier, in my opinion, to do this. So we can plot this. This is a density estimate again, so maybe we want to set false. And then we see it looks a lot more symmetric. It's not as skewed as it was before. Does anyone have any suggestions on what we still need to change for this plot? Y label is count, yes. Oh, another kind of trick. There's this text here, which is kind of annoying sometimes. If you don't want the text, end your code with a semicolon, and then it'll go away. That just a little quirk that can be kind of annoying to deal with. Change X label, yes, John says exactly right. So this is not the gross national income per capita anymore. Like, what is $3? That doesn't make any sense. So yeah, someone asked, where was the semicolon hack during the project? Well, better late than never. So instead of just saying gross national income, you can just say log of gross national income. Or if you really wanted to, you could say log base 10. And you get the idea. But always make sure to update your axes with what you're plotting. I've been a little bad about it throughout the lab. But always make sure to do that. Why do we use log 10 instead of ln? We can try to do ln. That would just be .log. And you see basically the same exact shape. It doesn't really matter a whole lot. A lot of times it's more intuitive to think in terms of base 10 instead of base E. X-axis change again, exactly right. You guys are keeping me on my toes. But you'll still see the same shape. But it's not super important what base you use. But a lot of times log 10, and log 10 has a more intuitive explanation than log base E does, which I think is explained later on in the lab. So there's the question. Again, if we wanted to set KD equals true, we could do all that, but you've seen that. So log does a good job of symmetrizing the distribution as it did before. Great. So on the other hand, long left tails are common with distributions variables that have an upper limit, such as percentages, like we see here with literacy rate. There's a bunch of countries stacked near 100. So instead of being right skewed like this data is left skewed. So it says in this case, we can use a power transformation, such as squaring or cubing the values. So in the cell below, make a distribution plot of lit with a data transform using a power. Awesome. So I'm just going to go here and copy this code. Unfortunately, a lot of this lab is just copying and pasting. Not super exciting. So we see here, let's get rid of this subplot. So here's our data, our same data as before. If we want to do a power transformation, you guys can just do, we call the two stars, and then to whatever power we want. So there's a square transformation. There's a cube transformation. And there's a fourth power distribution, a quartic power. Does anyone have any thoughts as to which ones are best? I guess I can try and show a bunch. So there's 2. There's 3. Which one kind of looks the least skewed, in your opinion? power 4, power 4, 4, 4. I'm seeing a lot of 4s. I would agree. Even 4 isn't the best because it looks kind of bimodal. We could even try upping it to 5. And 5 might even be better, to be honest. But by the time you run into 5, then you kind of lose your rationale a little bit. Like, what motivation do we have to take literacy rate to the 5th power, other than the fact that it makes a nice looking plot? Even the 4th power is stretching it a little bit, but that was one of the options they gave us, so that's what we're going to go with. And like before, we can use the semicolon, and then always be aware, 4th power. A little bit clunky, but again, matplotlib quirks. What is the rationale behind raising power in general? Yeah, so a lot of times, basically the rationale is for exactly this purpose, to kind of make our data set a lot less skewed than it was before. Because it is hard to tell what's going on, like what's going on in these bars where there are so many countries. We can't really tell a lot of information there. So when we do a log, that skews, or it takes right skews and symmetrizes it. But when you have data that is less skewed, you can imagine that now all of the percentages in here, so like 99%, 98%, now the difference between those will be a lot larger than, say, the difference between 2 and 3% or whatever, 20 and 21%. Because when we square, or take the 3rd power, 4th power, whatever, when we square those values, that kind of exacerbates the difference between the items, the percentages up here, more than it does the percentages down there. And likewise, or I guess the flip side for taking the log of less skewed data, it emphasizes the difference in this bar. So that's our transformations. Jinran, what do you think about jumping to question 2 now, since I took a little bit of time? Question 1D, it's a lot of the same as before, except now you're doing a scatter plot instead. But it's the same idea of using transformations to left skew, to like symmetrize and like undo the skew, so to speak, but just the scatter plots as opposed to histograms. Jinran, do you want to jump to question 2?
Yeah. Okay, cool.
Okay.
So,
and if you have any questions, I'll be active in the chat. So just for time's sake.
So like if you have any question about question 1, just like feel free to post them in the chat, and then like we will try our best to respond. Okay. So let's go to the second part of the lab, which is about the kernel density is that KDE? Yeah, kernel density estimation. So first I will try to share my screen.
Yeah, you should be able to now. I'm sorry.
Okay, yeah. Wait, did you enable screen sharing for everyone?
I have now. Sorry about that.
Yep, that works. Okay. So part 2, we'll talk a little bit about the KDE. So like basically we will implement a like density function in KDE, and also think about like how we use different like hyperparameter alpha will change the visualization of the KDE. So before we get into these specific parts of the question, we're going to kind of like do some sort of like the conceptual overview on the KDE. So basically the purpose of the kernel density estimation is that, so like we're initially given a histogram. So and we can use a probability density function to kind of like make the histogram like kind of like smoother and kind of like easier to visualize. So so like this slide is kind of like created from the lecture, so I will not go into the exact detail of how KDE works. So basically we will kind of like put a normal curve on each of the data point, and then we will kind of like normalize each curve, And then after that, so that the total area under like the sum of all these curves will sum up to 1. So like after that, we will summing up the kind of like the value of the different normal curves at each value of the x-axis. And then after that, we will kind of like get the KDE, so like the kernel density of the histogram. So like this will look like, so like this is an example of we only have 5 data points, and then we can just kind of like manually calculate that. So the kernel density function, so like this visualization, it will take into a value density function, which is called the kernel. So it must be non-negative for all the input, and it must also integrate into 1. So which means that like the total area under the new KDE will be 1. So like this will be similar to the idea of the histogram. So you can just think of the KDE as a way to smoothing the histogram. So the most common one is the Gaussian kernel, which we'll basically use in lab 5. And yeah, and also like there is one argument when we are doing the KDE. So it will be the alpha, which is called the hyperparameter. So just notice that like as alpha increase, the KDE will become more smooth, which is like, yeah, you can see that like in all these 4 pictures. Okay, so is there any like question on the conceptual part of the KDE? Let me see, is there anything in the chat? Okay, I see. Okay, cool. Then we'll first get into the question in lab 5. And if you have any question either on the lab question or on the conceptual part, just feel free to post them in the chat. So first here we have only 3 data points of 2 and 4 and 9. So here we'll make the histogram. So we see that like it will be pretty easy to do that because we only have kind of like it's kind of like 2 different shorthands. And yeah, and when we are plotting the disk plot, we can set the KDE argument to true. So this will automatically give us a KDE kind of like estimate. So you can see that like this smooth curve is just the result of like putting a small normal curve on all of these data points, all of these 3 data points, and then also summing up the value of the normal curve on each of the value on the x-axis. Let's see, is there anything in the chat? Okay, cool, yeah. Yeah, okay, yeah. Yes, yeah, so like the slides that I just showed to you, just the one from lecture 10. So just feel free to refer to them after the lab section on the course website. And okay, on the third part, yeah, and also like we can set the bandwidth, which stands for the bandwidth in the kernel density estimate function. So so here in the following function, we are setting the bandwidth value of 0.5 for each data point, and then you can see that like this will be quite different. So like previously we have a kind of like a pretty normal KDE curve after we set the KDE function, the KDE argument into true. However, now we have this kind of like pretty weird, this up and down KDE curve. This is because I think so like the width of the normal curve that you are putting on each of the data point is pretty kind of like is different from the previous one. So you can kind of like see different shape. So if you actually want to try, you can kind of like change the 0.5 into maybe 1 or something like that. And then see, okay, so like this will kind of like looks better than the previous one. So actually, if you're kind of like increasing the value of the bandwidth, and then you might say that like, oh, it will become more smooth. Yeah, say for example, if we change to 2, I think it will look, yeah, so like it will look much better. Let's see if there's anything in the chat. Yeah. And also, if we just like in the previous part, we don't set any argument to the bandwidth, and then it will just automatically generate the one that like not like notebook, like Jupyter notebook thinks like it will fit the most. Okay, let's dive into part A. So here, yeah, so like here we know that like we are using the Gaussian model here. So the Gaussian kernel model is kind of like defined for us. So it will take the alpha, which is the hyperparameter in the kernel density function, and it will also take x, which is the array of values of the variable whose distribution we're plotting. So I think here x will stand for some sort of like the any column of the data frame. And the z is the center of the Gaussian. So it will be the value on the x-axis where we are putting this small normal curve on the data point. So is there any question on the implementation of the Gaussian kernel model? Gaussian kernel function? Yeah, so basically it is just taking a data point and its x value, and it will plot some kind of like this normal curve on this data point that you specify. See in the chat. How, okay, so there's a question in the chat. How do we decide z? I think, oh, so like actually z, so like z is the center of the Gaussian. So for example, it is a data point or an array of data point. So I think basically you will pass in some value that you're going to plot just in the just when you are taking the array, I think. So it will be, for example, like say here we are calling alpha x, so like say here we only have 3 data points. So yeah, so like here we are plotting a Gaussian kernel centered at 9 with alpha like 0.5. So so for z, so I think it will actually work better if you have different center value for different data points. So here we are only looking for so like for example in this example we are only kind of like setting one fixed value for center of the normal curve, but like in the following question we can still kind of like passing in a numpy array as an argument for z. So it will kind of like adjust to different center for the normal curve when you're trying to take in a data array. So like actually for x in xs here, so it is kind of like iterate. So like this iteration will work on the data array. So it will kind of like iterate through each data point on the data array. But for the center one, as we will kind of like get through really quickly in the later question, you can still pass in an array as an argument for z. So in that case, it will have the like more flexible thing. Okay, so let's get into the first cell of the part A. So here we want to plot the 3 kernel density function corresponding to 3 data points. And it says that like we will first need to normalize the kernel. So similar to what so instead, so like different from the previous part, we want to plot 3 data points. So each of them, so the area under each of the kernel should be 1/3. And another hint is that like the Gaussian kernel function can take a numpy array as an argument for z. So actually the center of the normal curve will be different for each of the data point when you're plotting the kernel. And also you want to plot multiple plots at once. So you can use the plt.plot. Yeah, so something like that. So basically the code will be pretty similar to previous one. So I will just start by copy and paste. So however, what will be different here is that so first it says that like we'll need to normalize the kernel function. So I will multiply 1/3 for each of the value that the Gaussian kernel returns. And after that, it says like, so the center of each of the normal curve will be different when we are plotting all 3 data points. So actually the Z argument should be a NumPy array. So we have defined the data 3 point here. So we will use this NumPy array. And after that, I think we should be fine. Yeah. So here we're kind of like plotting 3 normal curve on each of the 3 data points we're given. So after that, we'll kind of like, and then we also normalize the value of the normal curve. So then the total area under each of the normal curve will be 1/3. And after that, okay, so after we plot each of the smaller normal curve, we want to summing up the value, summing up the y value on each value of the x-axis. So in this case, we'll do the same thing as before. But instead, we are going to summing but instead the y-axis is not a KDE curve. We want to sum up the value on each of the x-axis. So what we're going to do is that we can use the np.sum with argument axis is equal to 1. So in this case, what it will basically do is that say, okay, so say for example, we look at the, so we can look at the y value on the x when x is equal to 2.5. So it will adding up the y value of the green curve and also the orange curve and also the blue curve. So it will turns out to be the sum of all 3 curves, and it is exactly what we're looking for in a KDE like visualization. So we can say np.sum and np.sum with argument axis is equal to 1. Oops. Oh, wait. I should put it here. Yeah. So actually this is how, so like then if we sum this up, this would generate the KDE function of all the 3 data points. So any question in the question 2.8? Okay. So we will go into the question 2b. So okay, here we want to looking at the World Bank data, and we are looking at the log 10 of the income data from the World Bank. So this is something that is kind of like automatically generated from the this plot function. So this looks much better. And in this in 2b, it wants us to make a similar plot using the technique from question 2a. So give an estimate of the alpha value chosen by this plot function by twinkling your alpha value until your plot looks almost the same. So make sure to normalize your graph. So the area under the curve is 1. Okay. So basically it will be pretty much similar to what we have done in 2a, but instead we don't only have 3 data points, we have a lot of them. So actually we can, okay, so let's start by, so first, let's think about what we need to do. So first we are going to define an alpha value. So this is something that we don't know right now. So I can just like randomly set it to 1. And similar to 2a, we will need to have an array of the KDE curve. So in which case we will call the Gaussian kernel function and then normalize after we calling that. So I will basically copy and paste from here. It will be pretty much easier. We only need to change the argument. So so first we look at the Gaussian kernel function. So what will be the argument for the Gaussian kernel function? So xs is a data array that we get from the data point. So here we are kind of like plotting the log 10 of the income column of the data frame. So we can basically copy and paste here. So this will be an array. And after that, we are kind of like doing and then after that, z is the argument for the center of each normal curve that we are going to plot. So this will also be so this will actually be the same as the data array we're going to pass in because we want each normal curve to be centered at each data point. So we can copy and paste from here. And what is the purpose of 1/3 here? So in the previous example, we want to normalize. And since we know that like, we have three data points, so we just divide it by 3. But here, what is the number of the data points in total? So we are plotting the column of the income column of this data frame. So one way to get the total number of data points is using the length function of the series of pandas series. So we can just basically write the length of the data frame. So this will give us the total number of data points included in this data frame. Okay, so similarly, we are going to use the title and the X label. And after that, we want to use, and finally, similar to part A, we will use the plt.plot. And summing up all these values. So let's see whether it works. Oops. X and Y must have the same first dimension, but have the shapes 200 and 147. Okay, let's see. What's the problem? Oh. Oh, okay, I see. We think we should use this one instead of that one. Okay, this works. So xs is the line space. So actually, the purpose of defining xs here is to having a kind of, wait, is that what we're looking for here? Okay, cool. So the purpose of defining xs here is kind of like initializing the value of the x-axis. So we say that like we didn't choose a pretty good alpha value. So I will try to change the value here. So let's try to change to 0.2. Try a smaller one. Yeah. Oh, so this one is too small. Try to 0.5. Oh, okay, maybe 0.2 looks better. Okay. Okay, so I'll stop at 0.2 here. So this will kind of like looks much similar to the previous one than the value of the 0.501. See, is there a question in the chat? Yeah, so like I think the purpose of using xs here is just so like xs is kind of like serve as the kind of like an array of the value on the x-axis. So like maybe from 0 to from 1 to 6, and it will have like much smaller line space than the one that we get from the data frame. Okay. So so unfortunately, basically we're kind of like running out of time. So if you I will continue to cover the implementation of the KDE function here because this will be pretty important. So if we have time, feel free to wait for another couple of like 2 to 3 minutes, and we will try to finish that like as soon as possible. So here we want to implement the KDE function. So we are given the mathematical function, and then we want to implement that given all these kind of like 4 arguments. So it is pretty straightforward. So the kernel is a function. So and then we are kind of like what would be the argument for the kernel function? So it will be the x and all the data. So like it will be the data that we are going to plot. And then after that, we are summing up the kernel function value on each of the data point, and then take the average. So it will return. So first, we are going to call the kernel function on the x and the data, So it's kind of like pretty much similar to what we have done here. And so like it will actually take 3 arguments. So it will have the alpha argument, which is our hyperparameter, and the x is the each data point that we want to plot, and data is kind of like the data array. So we will kind of like call the kernel function on that, and then we want to take the so we want to sum up the value of the kernel function on each of the data point, and then take the average. So we want to take the sum, so like np.sum, and after that we are going to take the average. So it will be the length of data, similar to what we have done in the so like this will just be like generally the same with the list comprehension that we are doing here. So let's see, we return greater.try. Okay, that's pretty good. And after that, you can use this you can use our new KDE function to plot this World Bank frame, the World Bank data frame. See in the chat. Okay, cool. So I think basically after that, there is no question that you would technically want to finish in order to receive the grade, to receive the credit. So but like it will be a pretty good exercise after that, because it will allow you to look at like how the visualization will be different if you are using like different values of alphas. So I will highly encourage you to kind of like work on that later and look at like multiple plots that and also you can kind of like there's another definition of the box, so like boxcar kernel, which is also pretty interesting. So feel free to like play around it a little bit after the lab section. Okay, this is all for today's live lab. And
Jinron, could you scroll back up to the function just for a sec? Sorry.
What?
Yeah, just
okay,
people in the chat. Yeah, just freeze it there.
Okay. There's a question that is only Q to C will be graded. So definitely Q to C, just like this function one, will be graded because like there's a grade there's an auto grader after that. So for the question after that, I think basically it is visualization. So there's nothing that there's no new code that we'll need to fill in after that in order to get credit. So it's just a way for you to kind of like visualize how changing the alpha value and how changing the kernel function will kind of like change the shape of the visualization. So I think as long as you're running all those skills, you should be fine. Yeah. So just make sure that like your generated PDF will contain all those visualizations, and after that, it will kind of like upload it to the Grid scope. Can we go through one? Oh, I think basically we're running out of time. For question 1D. Yeah. I will stop my screen share. Oh, stop. Okay, cool.
Thanks for coming out. Take care, everybody.
There's one question in the chat. What is the free response? Is that free response? Oh yeah.